So the second video for section 6.3 partial fractions, we just continue working examples. We see another example for case one, and this is that the denominator factors into distinct linear factors and only one copy of each. In other words, there's no exponent in these x minus 5 or x plus 1 linear terms in the denominator, or there's an understood exponent of 1. Okay, so this is still a case one situation. Now, we check that the rational function is proper. So we look at the degree of the numerator, it's 1, the highest power of x. Down here, we'd have x times x, where we'd multiply this out. So we have x squared, that's 2. So this is a proper rational function since the degree of the numerator is less than the degree of the denominator. So we can decompose this via partial fraction decomposition. And in order to do so, we'll write our integrand, just the function, the rational function from the integral, over here by itself. And we'll know that it decomposes as a over x minus 5, choosing one linear factor, and then b over x plus 1, splitting over the other linear factor in the denominator. Now, were there a third term in the denominator, we could have plus c over that linear factor as well. So just as last time, a and b are unknown. It's just they're guaranteed to exist. So a and b need to be found. And the way we do that first, after we've set this up, is to multiply both sides by the denominator. We see when we do that against this term, the x minus 5's cancel, and we're left with a times x plus 1. When we multiply b over x plus 1 times this denominator, x minus 5 cancels, and we have x plus 1 cancels, and we have b times x minus 5. Of course, on the left-hand side, the denominator cancels fully, and we're left with only the numerator of 3x plus 5. Now we group our like terms. So in other words, there's an ax and there's a bx. So we'll add those together as a plus bx. And then we've got our constant terms to group, and that'll be an a and then a b times negative 5, so a minus 5b. And that's exactly what we see in this term. The reason for grouping the like terms is now we can establish a system of linear equations. This coefficient in front of x must be equal to this coefficient in front of x. Similarly, this coefficient, which is the constant coefficient, must be equal to this coefficient. And from that, those two equalities that must happen, we get two equations, and those are the ones below. And that's 3 equals a plus b, 5 equals a minus 5b. Again, this 3 is here, a plus b, and this 5 is here, and it's a minus 5b. So now we have a system of linear equations. We have two equations for two unknowns, so we can find a unique solution to this. And this time we're using substitution with a little bit of maybe new notation. We, in this step through the arrow, we've decided to solve for a in terms of b, and we see that we have a is equal to 3 minus b. Now we use that information to extend our lower equation, or to modify our lower equation, and we have a substitution for a, which fits in right here. A is 3 minus b, and that replaced this a. And then we have minus 5b that's already in that equation. But now this equation is completely in terms of b, and that's our substitution strategy for solving linear equations. Last time we did an addition or elimination method to add up the two equations and delete one of the variables. This time we're substituting. Either way is fine. Sometimes one is more useful or more quick than the other. So when we solve for b in this case, we have 3 minus 6b on the right. Subtract 3 from both sides to get 2 equals negative 6b, and that leaves us with b equals negative 1/3 after we solve for this term. Once we know that b is negative 1/3, we'll recycle this information. A is 3 minus negative 1/3. That's what's happening here. And we end up with 10/3. Now we've completely decomposed our rational function. So we can rewrite this integral of this more complicated rational function at the top as the integral of a over x minus 5, which a is 10/3. And we've already factored that 10/3 to the front of the integral. And then minus the second portion of this. This is b's decomposition. B was negative 1/3, so that's why we have a minus sign here and a 1/3 factor there, over x plus 1. So that would be negative 1/3 over x plus 1, but we factored the constant out to the front of the integral. So once we're here, we recognize that these are pretty straightforward integrals. In fact, any of these non-repeated linear factors in the denominator will always have a straightforward natural log integral that looks like this. And that's in fact what has happened here. So that's another round of case one. Let's have a look at case two. What happens if these linear factors in the denominator are repeated? So we have our general rule here, and they're showing that, just for instance, for an example, that our first linear term is raised to an exponent of r. So in other words, it's now no longer 1. It's repeated r times. Maybe that's a positive 2. Maybe it's a positive 4. If a linear factor has multiple copies of itself, or multiples of itself, perhaps, like say in this example, x minus 1 on its own, this term is a linear factor, but there are two of them times each other, and that's how we have that squared. So that's a repeated linear factor. It's not a quadratic because it's factored all the way down to a linear factor, but it's raised to a positive power, positive integer power. So when that happens, the way we'll decompose is as follows. We'll start to count up a1x plus b1, that's this repeated term, and we do so, and notice the exponent increments each time until we arrive all the way to r. So that means if this r was 4, that exponent was a 4, then we'd have 4 copies, a1, a2, a3, a4, over increasing powers of our linear factor. And we're going to see this worked out down below in the example. Probably a little bit more clear to see it there for the first time anyway. So we do our check for proper. Degree of the top is 1, degree of the denominator is 3, so it is proper. And next up, we write down our rational function. We don't need the integral for now. And we're going to decompose it as a over x minus 1. And note that the denominator is already completely factored. So it's easy to jump right to the decomposition. So it's a over x minus 1. And then since that is squared, we need to count up. The next one, we have a b over x minus 1 squared. Since that is the power of this linear factor, we can stop there. If it was cubed, we'd have to do c over x minus 1 cubed and stop there instead. But we copied all versions, all lower order powers of this up to 2. So we're good for that linear factor, and now we just need to take care of the other linear factor. Luckily, that's just to a power of 1. It's not repeated. So we have c over x plus 2. Now we have 3 unknowns, a, b, and c, but we'll have a very similar technique for solving for these, with possibly a new trick thrown in. The first step is to multiply both sides by the denominator. So the left-hand side just becomes the numerator. That's over there. And then on the right-hand side, this x minus 1 cancels with 1 copy of x minus 1 squared to leave an x minus 1 multiple here, and times x plus 2. Now b over x minus 1 squared, when we multiply through by this denominator, the x minus 1 squareds cancel, and we're just left with b times x plus 2. Similarly, c is x minus 1 squared. Now, there's a nice trick. When we look at, we don't always want to try to use this, but when it's available, we might as well. We look at the fact that this coefficient a and this coefficient c have x minus 1 in their linear factors. This has to hold for all values of x. So if we can input a value of x that zeroes those out, it should still hold there. The equation still has to hold there, only we might be able to simplify our given equation as is and solve for one of our coefficients, namely b, since it won't be zeroed out. So if we substitute x equals 1 into this, then we'll have a 0 here, so a times 0, a 0 here, so c times 0, and we just have b times 1 plus 2, right? We substituted a 1 for x here, and we got a 1 here plus 2. That being the case, we've got 3b on the right-hand side equals 9 on the left. Don't forget to substitute 1 for x here as well. We have 9, so we solve for b, and we have that b is equal to 3. It's a nice quick shortcut. It won't always be available, but it often is, so it's good to know. We can set x equal to any useful value we want in order to come up with at least one of these coefficients in a quick way. Now what we'll do is probably update this equation and then combine like terms and try to work from there. Or we notice we could probably play the trick again. X plus 2 and an x plus 2. How about we set x equal to -2, and then c won't be zeroed out, but the other two will, and we'll be able to solve for c. Then we'll know b and c, and then finding a could be that much easier. So let's go ahead and do that on the next page. So we set x equal to -2. And here's just a repeat of what our equation is, so we don't forget. And -2 times -2 plus 7, that's the left-hand side, substituted x equals -2. And on the right, of course, a and b have zeros times them, so they're going to fall out. This x became a -2 over here by c. We're squaring that, so we have -2 times -1 is -3 squared is 9c equals what happens on the left-hand side? -4 plus 7 is 3. So we have 3 is equal to 9c. We solve for c to get 1/3. So now we know b and we know c, and we can dig back into this overall equation to find a. So notice there's no tricks. If we try to zero out the other two terms, a is always going to become zeroed out. So there's no short way to get to a now. We're going to have to chase it down correctly. So we substitute for b the 1/3 that we found and 1/3 for c. So sorry, 3 for b and 1/3 for c. And then we notice that on the left, since we do have second degree terms over here, once we square this out, we might as well write as 0x squared, just so we keep our details straight. And we're going to factor everything out, expand everything on the right-hand side, and then combine our like terms. Once we do that, we see that we have a plus 1/3 times x squared is our x squared term. So that's going to match with this. And just to carry out the rest of the details to see them, this should be equal to 2, and this should be equal to 7. We can pick any one of these three equations to determine a, and they should all determine a to be the same value. So that's a nice thing to be able to check your work with. So in this case, this needed to be 0, so a plus 1/3 equals 0, so a is -1/3. Now we have our full decomposition. So for a, we have -1/3 over x minus 1. That's its decomposition term. You might have to turn back to the previous page to see the overall decomposition that we'd set up for our rational function. B is 3, and it's over x minus 1 squared. And c is 1/3, and it's over x plus 2. Okay, the first and last rational function in here are just natural log integrals. So we end up with these as our antiderivatives of those outer two. The middle one might look a little complicated at first, but we notice that a u substitution will do just fine. We let u be equal to x minus 1. So du is dx. Once we take the derivative of that, we get 1. And we can substitute that into this integral. Notice we've taken 3 over x minus 1 squared to be 3 times x minus 1 to the -2 power. Factored 3 out of the integral. And following up on the details, well, the reader can close up the details on this, but what we integrate to is we, remember, increase the power here by 1, becomes -1, and then multiply that, or divide by that new power here, and that's the same as multiplying by -1. So there's our answer to that one. Closed up. A nice u substitution sandwich between two natural log integrals. Sometimes these might be a little bit more complicated. Typically, a u substitution can get us out, especially for linear factors. Okay, so that was case 2, repeated linear factors. Case 3 is the denominator contains an irreducible quadratic that does not repeat itself. So in other words, let's look directly at this first example. The outside power of this quadratic is not greater than 1, right? It's just one factor or one copy of itself in the denominator. That's case 3. Now the linear factors that might be involved or may not be there. Well, they should be there if there's one irreducible quadratic. They're handled as normal, but an irreducible quadratic, remember that's a quadratic function that does not factor into two linear terms. There's just no way to factor it. One way to check to see that something is an irreducible quadratic is to calculate the discriminant. Remember the discriminant of a quadratic function that is ax squared plus bx plus c. Those are the coefficients, 1, 2, and 2. The discriminant is that inner portion of the radical and the quadratic equation, which is a quadratic formula, which is b squared minus 4 times a times c. So b squared minus 4ac. If that discriminant is negative, it has complex roots, so it's an irreducible quadratic. So that's your check to know that you have an irreducible quadratic. If it wasn't an irreducible quadratic, then what you'd be able to do is actually factor this quadratic function into two linear factors, and then you just have perhaps case 1 or case 2. Everything would be linear factors beneath here. But in this case, it is an irreducible quadratic. We'd also check that the degree of the top is 0. We see that. And then the degree of the denominator is 3 for x cubed. And we are, in fact, proper. Okay, so our decomposition. When we do have an irreducible quadratic, our decomposition is a little different. We write that irreducible quadratic in a denominator, and then above it, we introduce ax plus b. Right? Or in this case, a1x plus b1. All the other linear factors just do the same as they did before in case 1 and case 2, but for an irreducible quadratic, we must use ax plus b or bx plus c or cx plus d, wherever we are in the alphabet, or we'll use numbered letters like we see in the box. Okay, so let's pull our rational function out of the integral. We've written it down here. And write down our decomposition. This is an irreducible quadratic, so we write bx plus c over that irreducible quadratic. Okay, now we have a linear factor, and we'll just add a over x minus 1 for that linear factor. Now, we perform the same step as usual. We multiply both sides by the denominator, and we start to try to solve for b, c, and a. In our case, x plus 2 or x squared plus 2x plus 2 cancels with this. We're left with this term times x minus 1, and a will be left to be multiplied by the irreducible quadratic after all the cancellations that have happened. And once we do so, we notice that if we let x be equal to positive 1, we'll zero out all of this term. So that's nice. It doesn't affect the left-hand side because there's no x over there. So 5 is equal to a times plugging in 1 to this irreducible quadratic, and it turns out that this is equal to 1 once we've done that. So 5 equals 5a, and we have a is equal to 1 in this case. So that's an easy one. We got a out of the way. Now we're going to have to do some work to find b and c. It's very similar work. We just group like terms and equate our coefficients. So 5 is equal to bx plus c times x minus, we're resetting our basic equation here, and we're going to work forward. We're going to say that a is equal to 1. We'll use that information. So we'll just have normal constants in front of this portion. And we're going to collect our like terms, like I said. So we have bx squared plus x squared is b plus 1x squared. And then see these equations for x, negative bx plus cx plus 2x is negative b plus c plus 2 all times x. So here we are grouping our like coefficients, and the constants follow somewhat similar. It looks like negative c plus 2 are our only constants. On the left-hand side, we still have 5. So we write down 0x squared plus 0x as placeholders plus our constant 5. When we equate these coefficients, once all the like terms have been grouped, we see that b plus 1 equals 0. We see that b is negative 1 thanks to this equation. So we can jump out of this nice and quickly and update things as we move along. We can also look at, I'm actually going to ignore this middle term simply because we can use negative c plus 2 is equal to the constant 5. And we could have pursued it through here by letting b equal to negative 1 and equating that to 0 with this one. But Whatever is more handy is suitable. So we find that c is -3. So we've got our full unknown coefficients. We're ready to write that down in our decomposition. And what we arrive at, well, a is 1. So here's our simple one over here. We've already split the sum up from the integral. And we've got a trick to do with the other one. This is, of course, the highlighted one's going to be natural log of x minus 1. There's not much to worry about there. We're getting used to that by now. Now, on the other hand, we have negative x minus 3 over x squared plus 2x plus 2. These aren't ever really very clean, but they're not ever really very different from each other. Once you've done this technique a few times, you'll be somewhat used to what you need to do when you get to this point. So it looks like we've considered a u substitution off to the right here to see what we might be able to do. And that's because maybe what we think about is the fact that this integral, or this numerator, if we have the constants right, since this is a linear function, if we have the constants right, it might just be the derivative. We might be able to get a du out of u equals x squared plus 2x plus 2. That's our goal. We have two minus signs in the numerator, so we factor those out to in front of the denominator and just make that a positive x plus 3 in here. The next thing we do is say, let's split up x plus 1 or x plus 3 as x plus 1 plus 2. Now, the guide for doing that, the reason we want to do that is because we've already thought, let's make a u substitution for this term, since it's 1 degree above the numerator, and see if we can manipulate things to make this work. Du is 2x plus 2 when we differentiate our u. So we factor 2 out, we have 2 times x plus 1. That means if we can get just an x plus 1 in the numerator, that's a good du for this portion of this integral. Okay, and we'll probably have to split the numerator with the plus 2 by itself over that denominator, and we'll have another integral that comes from there. So that's exactly what's happening right now. Dx is equal to du over 2 times x plus 1. We see that off to the right, and that's our substitution to plug into this. So dx will swap out for 2 over x plus 1. This will become u. So x plus 1 dx are times 2 over x plus 1. That gives us a 1/2. The x plus 1 cancels with this x plus 1. Because, of course, we're just substituting that highlighted dx into our integral over here. And what we arrive at is that 1/2 from down here. We just push it out front. And the only thing that survived this was du and the fact that this is u. So we just have the integral of du over u. That's going to be natural log of u. We back out of that substitution since u is this quadratic function, and we get this term down here. So we've left one thing by itself. We peeled off that plus 2 because it was inconvenient to us in the moment of working on this. So we still got this minus 2 over that denominator integral. The way to get through this one is to complete the square on the lower portion. This will be an arctangent integral. And let's see some of the details for that. We complete the square in the denominator, and we also just factor 2 out in front of the integral. It doesn't matter. It'll just be a 1 over whatever this is, and that's what we want to be able to work on this. But we complete the square down here. Remember, we take half of 2 to complete the square and square that. So half of 2 is 1. 1 squared is 1. So we're going to add and subtract 1 down here, and that's inside or next to that plus 2 that's down here. Once we've done so, we know that we can factor this portion, the x squared plus 2x plus 1 portion, and that becomes x plus 1 squared. And the negative 1 and the 2 add up to be a positive 1. So we have x plus 1 squared as a group plus 1. Now that's a u substitution, but since we've already had one, I've used a v substitution, and that's v equals x plus 1. And then the integral of that is dv equals dx. So the reason this works out nicely for us is because we have a 1 coefficient here. If we didn't, we would have just factored that out as a denominator constant here. And we've we can make a u substitution as v substitution so that it's 1 over v squared plus 1. And remember that the integral of 1 over v squared plus 1 is arctangent of v. Or we're just using the fact from a couple pages ago about preliminary integrals. So this is -2 times arctangent of x plus 1. All the rest of these integrals have been handled. We have a plus c at the end. And that is about as complicated as it gets. So that's the good news. The bad news is you see there is some stuff to negotiate. It's going to take some practice to know these moves and to get them right. But this is, once you've seen this example, you've essentially seen the path for all of them. It's just a matter of getting the details right for yourself when you work on these problems. So let's see case 4. Case 4, we're just asked to break down or to decompose one of these without actually finding the coefficients. Finding the coefficients oftentimes is the heavy computation part of these things. So let's just see what to do when we have irreducible quadratic factors that repeat. In other words, which repeat. So say in this case, we have an irreducible quadratic to a power of r, which is greater than 1. Well, what we do in this case is very similar to the repeated linear factors. We write one version with its decomposition, then we need another pair of decomposition constants, and we step up to squared, to cubed, to the 4th, until we reach our power here of r, whatever that number might be. Okay, all the while writing down our new letters of the alphabet or numbering our A's and B's appropriately, accordingly. So let's see, in this example, they just ask us to write down the decomposition, but don't try to solve or evaluate for the coefficients. This is a common way to test your knowledge and ability with these problems without actually having to do all the full work of this. So we have 1 over 3 minus x to the 4th over this linear factor times a repeated irreducible quadratic. You can check that this is an irreducible quadratic through the discriminant, or you just try to think of a real number x that solves this, in other words, makes it 0, and you realize there isn't one, and it's plus or minus I that you square to get -1 to make that 0. So it is, in fact, irreducible as a quadratic, and we are proper because this is x times x to the 4th as our lead term. That's x to the 5th, which is a greater degree than x to the 4th. So our decomposition, we know that this will decompose as a over x minus 2. And now we look at our irreducible quadratic, and we do the first power of it, x squared plus 1, with a bx plus c, a linear term above that. And then we step it up, x squared plus 1 squared, and we move along to dx plus e. Right? We're just moving down the alphabet in this case, but notice that these irreducible quadratics always have linear decomposition terms above them. Linear decomposition terms always have constant coefficients above them, constant decomposition terms above them. So even when these linear ones are squared, we still just use a single letter. There's no ax plus c or anything like that. Okay, so keep that in mind. And down below, we see an extended example. What would happen if this was x minus 2 squared or x squared plus 1 quantity cubed? That's nice to just see it all in action here. We'd have a1 over x minus 2 for the first power of this, counting up until we hit x minus 2 squared. And notice we put another a here. Again, these linear factors just have constants above them, as I stated before. And now we have to count 1, 2, 3 to get up to this one, using linear factors for each of them. And you see the powers of the irreducible quadratic increment until we hit the 1 in the original denominator. So that's the technique. Those are all 4 cases. Now, of course, this could be a nightmare. This problem here, especially, this one's not even very friendly to go about finding all the coefficients to. There's quite a bit of work to find these coefficients. So I don't think we have many problems that will help you find 5 undetermined coefficients. We certainly don't have any that would make you find this many. But those are just big linear systems. All the tricks you can come up with to get through those will help. But practice really goes a long way in this. So this is really a straightforward section. 4 cases here. It takes lots of practice to become adept at this, but maybe rewind the video, watch portions that you need to see again, especially for the last example before this one, to really get the details of what to do when it's very mixed up. But otherwise, Practice makes perfect, and this can be a really nice technique to have in the bag, and it's not as hard to learn as you might think it is.